Look up on a clear day, and the sun appears as a quiet, constant fixture in the sky. But that stability is an optical illusion. You are looking at a violently unstable object, a sphere that generates enough energy every single second to power our entire civilization for over 600,000 years. Standard combustion requires oxygen and a chemical fuel, the basic ingredients of fire. In the vacuum of space, neither exists. The heat we feel on Earth is the product of physics far more complex than a simple chemical burn. Inside the sun, temperatures are so extreme they create a fourth state of matter called plasma. Atoms are literally stripped of their electrons, leaving behind a highly charged, electrically conducting soup of ions. Because this plasma conducts electricity, it interacts with massive magnetic fields. This allows solar material to churn and flow, functioning as a complex, self-regulating nuclear reactor. Understanding our star requires viewing it as a massive, functional machine, a system specifically tuned to transform millions of tons of matter into raw kinetic power. The conditions inside the solar core are physically impossible to replicate in a sustained way on Earth. The temperature hovers around 15 million degrees Celsius, and the plasma is crushed to a density roughly 150 times that of liquid water. Under immense pressure, hydrogen protons smash together, overcoming natural repulsion. They fuse into helium, releasing radiant energy. This doesn't happen one atom at a time. Every second, the core crushes 600 million tons of hydrogen in a continuous chain reaction. But if you weigh the resulting helium, the math doesn't quite balance out. 4 million tons of matter go missing in this process every second. Following Einstein's physics, that missing mass is converted entirely into pure energy. The sun is literally destroying itself. It sacrifices 4 million tons of its own mass every second to generate the light that illuminates our solar system. The pure energy born in the core does not get a straight shot out into space. It first has to push outward through an incredibly dense internal layer known as the radiative zone. The particles here are packed so tightly that a photon of light can only travel a few millimeters before crashing into an atom and bouncing off in a random direction. This random walk is so inefficient that it takes hundreds of thousands to millions of years for energy to clear this single layer. The sunlight warming your skin today is actually the exhaust from nuclear reactions that happened deep underground before early humans even existed. Once the energy finally escapes the dense interior, it hits the convective zone. Here, the plasma physically boils in massive columns, twisting and stretching the star's magnetic fields as the heat rises to the surface. When the energy finally breaches the surface, the photosphere, it creates intense magnetic volatility. The strong, twisted magnetic fields block rising heat, creating temporary dark blemishes about 1,500 degrees cooler than the surrounding plasma. We call these sunspots. Eventually, those tangled magnetic fields stretch too far. They snap and violently reconnect, triggering solar flares that dump the energy equivalent of 1 billion megatons of TNT into space in a matter of minutes. A peaceful afternoon in the sun is actually the highly filtered byproduct of an ancient, violent magnetic struggle inside a massive plasma reactor. Earth does not sit safely outside of this reactor. Our planet orbits entirely inside the heliosphere, the sun's extended volatile atmosphere. Earth's magnetic field acts as a protective shield against normal solar wind. But extreme explosions, known as coronal mass ejections, hurl billions of tons of magnetized plasma across the solar system, and they can blast right through our defenses. In 1859, a massive solar storm called the Carrington event overwhelmed our magnetic shield. The resulting atmospheric electrical currents were so strong that the global telegraph network physically sparked, shocking operators and setting paper to fire. Today, those same geomagnetically induced currents threaten to trigger a global internet apocalypse. While local fiber optic cables don't conduct electricity, long-haul undersea internet cables rely on copper-powered electronic repeaters to boost their signals. A severe coronal mass ejection could surge through the ocean, burning out these repeaters and instantly disconnecting continents for months. The star that fostered our biological evolution holds the active power to cripple our entire technological civilization in a matter of hours. The Sun has held a relative equilibrium for 4.6 billion years, but its core is accumulating helium ash from all those nuclear collisions, causing it to slowly and steadily heat up. In about 5 billion years, the core will exhaust its primary hydrogen fuel. Without that steady outward radiation pressure, the core will contract, heating up so drastically that it will force the star's outer layers to violently expand into a massive red giant. This swelling inferno will completely swallow Mercury and Venus. Earth might technically escape physical engulfment if its orbit shifts outward, but our oceans will have boiled away roughly 1 billion years earlier, simply from the Sun's steadily increasing brightness. We exist within a system of perfectly balanced chaos. Every sunrise is a nuclear event, and another tick on a clock counting down to the world's eventual consumption.